Hello everybody, thanks for joining us for another video here at Everything EE. Don't forget to like and subscribe. Today we're talking about debugging I2C, and so this will be the first in I guess a video series about debugging. And this is always a great subject when you're talking interviews, normal just working hours. Debugging comes into play a lot. So one of the things I'd like to show you is kind of a few things about the I2C data interface that a lot of sensors and memory devices and other sort of peripherals you're going to use when you have two modules on the same board. A lot of times I2C will be the communication interface that they use because it's pretty simple. It's three wires, one of the wires being ground. So at the end of the day, it's usually two traces that you have to run on your board. So it's actually pretty simple. Um, so it looks something like this. You have two data lines. You'll have SDA, and that's the bidirectional data going back and forth from master to slave. And then you have an SCL. And then, of course, you have ground. Okay. SDA is kind of interesting because it's bidirectional. So over here, you'll have your master device. And then here you would have your slave device. Right? But what kind of happens is, since it's bidirectional, you have some logic, so a buffer coming from over here, so that data can go this way. And you also have uh, the ability to send data out through this, what we call open collector output. Okay? So data is going out here, and data is coming in through this buffer here. Um, then you have your clock line. So this is just your clock line. It also is in this open collector output to slave device. Hopefully this doesn't get too messy. Right, slave it out here, and he has this clock signal. All right. And of course your ground. You got your ground. All good there. So the first thing you got to think about is how are we getting solid outputs here? Because if we see here, these guys are just floating around. So um, on all I2C interfaces, what you're gonna see is there will be pull-up resistors. So you'll see that all the time. That's just how I2C works. And usually you want to go with the largest pull-up resistor you can put. And the reason being is that, let me just redraw this a little bit so you can see. So right, you have your pull-up resistor here, and you want this to be as big as possible. The reason being here is that when this switch is turned on, this switch being the FET, when it's turned on, you have current going through here, right? And we know we want to minimize power in our circuits, especially if we're using this on a battery powered device. We want to be as low power as possible. And sometimes, it comes down to how much power are we using per byte sent on the I2C data bus. So we want this, our pull up, to be as big as possible because we want to minimize this current coming down through this resistor and then through the MOSFET. All right. But the issue, so all that being said, a lot of people will go with 4.7K, pretty standard for I2C um, data buses. Excuse me. Um, but a lot of times, what happens is uh, we in an actual system, what will happen sometimes is we'll have the master connected to a few slaves, because the beauty in I2C is that we can daisy chain these slaves. S for slave, right? Slave 1, slave 2, slave 3, and so on. This is really useful. We're able to have multiple devices on the same data bus, and we're basically communicating to these guys through an address. So you'll see addresses on the data sheets for these I2C devices, and I'm totally just making these up. They're usually not just 0, 1, 2, and 3, but they'll usually have a 2-digit hex value that's associated to their address. But what happens here at a hardware level is when you add more devices to your I2C data bus is you're also adding capacitance to that data line. So what we expect to see on this, if we were to take an oscilloscope, we were to scope this, we'd have VCC here, and this would be just ground. We would expect to be seeing something like this. Full swing of the data signal, nice and clean, that kind of deal, right? But what we might see is this. We might see something like this. The point being is that the signal is not swinging all the way to ground. So you'll see this eventually at some point in your career or in school. We'll get something like that. So the black is what we want. We want a full swing from VCC to ground, and the red is what we're getting on our scope. We're getting, I don't know, well, let's say this is like not even half VCC, right? So this is like VCC over 2. So it's like half of VCC. It's not even touching that. And so we know with our logic levels that there's a minimum required of swing to get a VOL, or a output low. So a lot of times what you'll get as your output here is you'll start seeing 0x, like FFF, right? Which is all ones. You'll start reading out all ones because you're never seeing anything swing low enough to VOL. Maybe VOL is somewhere down here. VOL is output low when the device is reading an output low. So it's not swinging far enough, right? And why is that? Well, we've put this 4.7K resistor here. We have some capacitance on this line over here from all these devices. So what's actually happening is you have this RC time constant. You have it like a tau, right? I think it's 1 over RC. So you have this time constant, 1 over RC, and basically this R is too big. It's making the time constant too long. So you're not giving it enough time to get down to the full swing all the way down to ground, right? So what we can do is we can go ahead and step this down. Usually what I'll do is I'll go from 4.7K and I'll go ahead and drop in a 2.2K. That's what I'll do. And, most of the time, that's the issue. You'll end up getting rid of uh, this swing that's not enough, and then you'll see that full swing from VCC to 0. So hopefully that makes sense for everyone. What you call this here is a weak pull-up. It's too weak. You need a stronger pull-up. You need to allow more current to flow to reduce that time constant that's arising from the capacitance applied to the line by multiple I2C devices. Or you might just have a device that's weird and it has some big internal capacitance on that I2C line, and sometimes you just have to bump that down. So, once you find that, usually going from 4.7, that 4.7 is really standard. You'll see that a lot. Then, if it's too high, you drop down to 2.2, and if you really need to dial it in, you can dial it in from there. All right. One other thing I wanted to mention is an easy way to kind of get this plot here. A trick you can use on your oscilloscope is you'll want to on SDA and the SCL lines, you'll want to probe here. Oh man, this might get a little weird. So probe there, probe here, and then on your SCL line, what you'll do is you will set a trigger on your oscilloscope. It should be a falling edge trigger. So let me just falling edge trigger. You'll set a falling edge trigger on your SCL, and then you'll have your probe on SDA. And the cool thing you get out is you'll have pretty much you'll have something like this as your clock. And then say we sent over a byte that was 0x. Let's go with something easy. Let's go with 1 1. So then what you would get is something like this. We have a 0, 0, 0, 0. Whoops, 1. Then you have a 0, 0, 0, 1. Alright, so pretty much on each one of these edges is where we're kind of reading the state of the SDA line, because the devices are being triggered by this clock signal. So if we put this into binary, it should be 0, 0, 0, 1, 0, 0, 0, 1. So here we have 0, 0, 0, 1, 0, 0, 0, 1. And this is SDA. And this is SCL. Okay? So that's how you would use your oscilloscope. You would set a trigger on your SCL data line to then be able to read out what's coming in on your SDA line. So it allows you to easily kind of take a look. And there's other fancy devices. There's I2C data bus reading devices that will straight up just output the hex value of the bytes that are going across the data line. But if you don't have that on hand, or all you've got is an oscilloscope, then you're going to want to turn to this kind of method, applying a trigger on your SCL line to then be able to see what's being sent on the data line. Okay? So you'll see this, just based on what the byte is being sent out. You'll see. So like, if it was 3, right? Let's do something like 3 where now we have a 1 1. Then what's gonna happen here is you'll see something like this. Whoops. It's okay. So we're expecting 1 and 1 and 1 and 1. So you'll get 0 0, then it'll hop up like this, and it'll look something like this. All right. So that's how you can sort of read out what you're getting byte by byte. Okay, guys. If you have any other questions about I2C or any other kind of debugging questions, please let me know down in the comments, and I will definitely help out and get y'all's questions answered. All right. Thank you. Have a great day.